So hello everyone. So in this video I am going to discuss how we can design a voltage regulator circuit using Zener diode. So as you know that Zener diode is a heavily doped PN junction diode which is specially used for breakdown purposes, and when the breakdown takes place the voltage across Zener diode is almost constant. So you can see the IV characteristics of a Zener diode. In reverse bias, the IV characteristics, see there is a breakdown region. Okay, so when you are applying a sufficiently high reverse voltage, so here, okay, so there is a sudden increase in a Zener current, and this region is basically the breakdown region, this region. And see, when the breakdown takes place the current increases rapidly and the voltage across Zener diode, so that is almost equal to the breakdown voltage. So we can use this breakdown property to design a circuit, so that is called a voltage regulator. As you know, the regulator means it will provide you a constant output irrespective of the input or the variation in the load resistance. So there may be two different cases. Suppose this is your unregulated supply voltage. So the value of this unregulated supply voltage may change depending upon the condition. Suppose you are taking this this VI is coming from output of a rectifier. Okay. So when the primary side voltage of a transformer changes, so of course the secondary side voltage will change and the rectified output will change. Okay. So this unregulated supply voltage is a function of your main AC input voltage. So we need to regulate that thing. That means to drive an electronic gadget, the first thing is that you need to provide a constant DC output. And there may be another one case. Suppose this is a load resistance. The resistance you are connecting at the output side, the value of the resistance may vary. Sometimes we are connecting a lower value of load resistance, and sometimes we are connecting a higher value of load resistance. So when you are connecting the load resistance, and depending upon the variation of its load value, the load current will vary. Okay, so as a result there is a chance that the output voltage will vary, because the output voltage V0 is nothing but IL into RL. Now see, using the Zener diode, how we can minimize those variations, and this device is basically a simple voltage regulator. Okay, now let us see how it works. Now coming to the circuit description, the input is the unregulated supply voltage and this is a resistance. Okay, and see the Zener diode, it is connected in the reverse bias because we are going to use the breakdown property of a Zener diode. Okay, and the IZ is the Zener current, VZ is the breakdown voltage of a VZ is basically the breakdown voltage of a Zener diode, and here that output voltage is a V0, RL is the load resistance, and IL is the load current. Okay, and so if we point out the value, different values, suppose the I is the current flowing to this resistance. So if I apply KCL at this point, so we can write, so let this is node X. So incoming current is I, so outgoing current we are getting IZ plus IL. So this is the first equation we are getting. And another one equation we can check what is the value of I. Okay, so the current flowing to the resistance I, so this is nothing but the potential difference between 2 points. So this point voltage, this is VI. So this point voltage, that is, you can write VZ or V0. Okay, so it is VI minus VZ divided by, you know, that resistance value R. So this is another one equation. And the third equation we can get from the circuit, that is output voltage V0. So this is nothing but load current IL into load resistance RL. Okay. So we can explain the working mechanism of the Zener diode voltage regulator using 3 equations. So let us see how we can explain that. Again I am drawing the circuit. So we have the regulator circuit here. And this one is the load resistance RL. This is R, this is our VI, and this is a Zener diode. So this current is nothing but IZ. This current is our load current IL, and the voltage across output, that is a V0, and the Zener diode voltage is VZ. You already know all those things. Okay. Now if I mention two different cases, suppose case 1, when input voltage V in changes. See, when there is a variation in V in, so how the Zener will provide the output voltage? It will try to maintain a constant output voltage. See, suppose when V in increases, okay, when V in increases, sorry, this is V in, okay, V in increases, so we know that the current I is equal to V in minus Vz divided by R, where Vz is the breakdown voltage of Zener diode, that is constant. Let you are using a 4.7 volt Zener diode, so Vz is constant. Okay, so when the value of V in increases here, the V in parameter increases and R is constant, so of course I will increase as per this equation. So I will increase. So when I increases, now we know that I is nothing but summation of two current, Zener current plus load current, I equal to Iz plus IL. So when I increases due to the increase in a V in, so I also increases. Now we need to maintain a constant output. So our target, because it is a regulator, so we need to maintain a constant output, that is V naught will be equal to IL into RL. So we need to maintain a constant load current. So IL will be constant, so whatever the changes, whatever the increase in the current I, so that extra amount of current will be bypassed through the Zener diode. Okay, so the variation in current is 5 milliampere. So the amount of current, okay, so the amount of current flowing through the Zener, okay, it will be the same amount. Okay, see here. Okay, so when V increases, I will increase. I increases means that the extra amount of current, okay, that will be bypassed to the Zener diode, that will be the same of I. Okay, so the extra amount of current will be bypassed through this when the value of V in increases by maintaining a load current constant, and therefore it will provide you a constant output voltage following this equation. Okay. Similarly, when V in will fall, what will happen? That that Zener current will reduce from its previous value. But in this case, you need to remember one thing. So you have to make sure that the Zener diode is in a breakdown region, because without breakdown it cannot work as a regulator, because the regulation property will get due to the Vz. Okay, so suppose the breakdown voltage of Zener diode 4.7 volt and you are applying a voltage of 4 volt, so definitely the breakdown will not take place, and then in that case you will not get the regulated output. So you have to make sure that the breakdown takes place. Okay. Now coming to the second point, that is when load changes. So again, there is a probability that there is a variation in load resistance. Okay. So sometimes you may connect a lower value of load resistance, sometimes you may connect the higher value of load resistance. But for this analysis, we consider V in is constant. So we cannot analyze both cases together. So here also case 1, when input changes, that is load constant. So for case 1. So for case 2, V in is constant. So now when the load changes, keeping V in constant, so if V in is constant, of course I will be constant, because I is nothing but V in minus Vz by R. So when our V in input voltage is constant, of course this one is a constant parameter, R is constant, so I will be constant. Now following second equation, I equal to Iz plus IL. Okay, now if I is constant, now let us see when you are applying, when you are connecting a lower value of load, then what will happen? Lower value of load leads to what? Higher value of load current. IL will increase when you are connecting a lower value of load resistance. So of course the current will increase. Okay, so IL will increase here. Okay, but the I is constant. What will happen? So Iz will fall in the same way. Okay, because the I is constant due to the constant V in, so I is constant, so Iz plus IL is constant. So when IL increases due to the lower value of RL, load resistance, so that the value of Zener current will reduce by the same amount. Okay, so that the total I will be constant. Okay, so in that way, the Zener will provide a constant output voltage. Okay. Second case, Similarly, you can explain this for a higher value of RL. Let we have a higher value of load resistance. So of course, when you are connecting a higher load resistance, that leads to a lower value of IL. The load current will fall, but the total I is a summation of IZ plus IL. So when the load current falls, of course the Zener current will arise, and ultimately IZ plus IL, the summation result I will be constant. So in this way, the Zener diode will provide a constant output voltage, but remember that the output you are getting, that is not 100% constant. So when you are varying the V in, or whenever you are varying the load resistance, okay, there is a slight variation in a V naught. So that parameter we can check by checking the performance matrix of any regulator, that is called line regulation and load regulation. So those are the different performance parameters. By checking those things, we can check how the regulator performs, whether it is working well or not. So what is line regulation? So we can say roughly, so line regulation means when your input voltage changes. Okay, so suppose your input voltage so is one input voltage. Okay, so V naught. So how to calculate line regulation? Suppose the output voltage you are getting V naught when the input is let V in 1 minus V naught at a different input voltage at V in 2. So that means the output you are getting when input is V in 1, the output you are getting when input is V into 2 different input divided by the output you are getting at V in 1, okay, into 100%. So this is all about line regulation. Now for ideal regulator, see, whenever there is a variation in input voltage, that means for two different value of this one and this one, the output voltage will be constant. Whatever the value of input voltage, the V naught will be constant. So for ideal case, so the value of this line regulation will be how much? 0. But for practical cases, okay, it is not 0, it is having some finite value. So lower value of line regulation is always desirable. So similarly, you can calculate another one parameter, because we have another one case that is called load regulation. So what is load regulation means? V naught at RL1 minus V naught at RL2 divided by V naught at RL1. Because, so load regulation is nothing but when you are connecting it to two different value of a load. Suppose one, the load value is let 100 ohm, another one case the load value is let 500 ohm. So what is the variation in the output voltage? So if your regulator is ideal regulator, then there should not be any variation. So when you are connecting to different value of a load voltage, load resistance, so the V naught will remain same. So again, for ideal case, load regulation will be 0%. But for practical cases, so definitely it will have some finite value. It is not 0. So this is all about the Zener diode as a voltage regulator. So see, once again, see the circuit. So we have two different cases. Case 1, when the load is constant, line voltage changes. Case 2, when the input voltage, that is line voltage, is constant, the load resistance, that is RL, changes. Okay, and this is the circuit, and those are the governing equation by which we can explain the working mechanism of this Zener diode. Thank you all.